Yeah.
What did you just press?
The charger.
I didn't realize it wasn't charging.
Okay. So
Yes, I have
formal.
this.
So satisfying. Yeah. Yeah, cool. Oh, cool, I guess.
Yeah, sure. Is there anything you can wrap around your neck or anything?
Oh no, this one's more hands-on. There's this one.
That work?
Yeah, stand here and talk.
I can stand here.
Yeah.
I can stand. Oh yeah. I mean, it's the same, I think.
Yeah. Sorry for the delay. Just now, Sue's Coffee, they forgot to make how to make matcha. So it took 20 minutes. Okay.
30 minutes.
30 minutes, yeah. Yeah. Okay. Anyway, I guess it's all should be fine. Like,
It should be fine.
Yeah.
You want me to start now? I know you said 6:15
Yeah.
now, but
yeah, I guess you can start now.
you can start now.
Yeah, you can. Yeah, you can. You can. Anyway, so okay, good afternoon, everyone. Right, don't have to be so formal. This is an undergraduate talk. But basically, this our friend over here, Ariff, right? So he's from Malaysia, okay, and then he went to Imperial College London, studied there, and recently graduated and came back here. So it's like wandering around Malaysia, right, looking at some of the map around Malaysia, and then came here. So yeah, he probably saw him last time during study group. Okay, just chatted around and then yeah, had fun, I guess. So without further ado, let me just pass the mic to Ariff and then we can begin. Yeah. All right.
Thank you so much. Hello, everybody. Can I just get an idea of like who is actually attending this talk? Because I wasn't very sure how to set this up properly. Like who here is in year 1 right now? Just to raise your hands. Year 1 students. 3, very brave. Year 2 students. Thank you. Year 3.
Some of them,
Yeah.
I think.
And anyone above that, master's, PhD, anything. All right, thank you. And just as well, I wasn't sure whether to start this by talking about topological spaces, but I'm just going to accept that all of you sort of have an idea of what a space is supposed to be, even if you don't have the formal definition. So this talk is about Morse theory. I first came across it when I was in first year, because really the ideas involved here are very, very easy. It's sort of the application which makes it very profound. Morse theory was introduced at some point, I think in its modern form in the 50s, and then developed by the likes of Thom, Smale, Witten, and in the 21st century, it tends to take the form of what you might call flower theory. So the underlying idea of Morse theory is that you can study a space, not directly, because that it tends to be very difficult, but rather by studying functions on that space. And in particular, consider this sort of like a donut shape. You imagine sort of like a sphere that you like dent down the middle. You end up getting 2 maximum points, 1 saddle point in the middle, and 1 minimum point. And these are critical points of what you might call a height function. So down there is the lowest point and up there is the highest point. So you have 2 local maxima, 1 saddle point and 1 minimum point. These are critical points of that differential equation right there, where the derivative is just the negative gradient of whatever the height function in this case. And when you set this up, the first thing you might notice, you play around with it, is that the number of maximum points minus the number of saddle points plus the number of minimum points is 2. Right? It's 2 minus 1 plus 1. And no matter how you try to deform the sphere, you add a bunch of bumps and all of this, that number 2 is constant, no matter what. You might be familiar 2 as being the Euler characteristic of a sphere. If you did your graph theory, you might recognize this as the number of vertices minus the number of edges plus the number of faces is 2, is the exact same number. And this turns out to be a genuine invariant of your space. The trick here is that the differential equation defines a sort of gradient flow on your space. You can see those like yellow arrows going from the maxima down to the saddle point and then down to the minimum. The core idea of Moore's theory is that locally you can model these kinds of differential equations with quadratic forms. If you start with a function, right? By a Taylor expansion or whatever, you have a sort of constant term, you have a linear term, you have a quadratic term, and then cubic and so on. If you look locally at a critical point, say at the point of index 1 there, the saddle point, you can say that the constant term is just 0 because we say that's the origin. So it's fine, constant term 0. You can say we look sufficiently close so that all the cubic terms and higher are 0. And because it's a critical point, the derivative is 0. So that's 0. Which means that it's only the quadratic terms that matters when you're looking at critical points. You might be familiar from like, secondary school maths that if your second derivative is positive, then you're a minimum point, and if it's negative, you're a maximum point. But so this is just a sort of a high dimensional generalization of this idea. So locally around this index 1 point, you can see that there are 2 flows going in and then 2 flows going out. So locally, the behavior kind of looks like this, I don't know what you call this, like a saddle point behavior. And locally, it just looks like negative x squared plus y squared, the function. Because if you differentiate that, of course, you get negative 2x, 2y, like that. And this is your gradient vector at all points. Okay. The idea here is that we can reconstruct the space based on the data of these flow lines. So the minimum point kind of looks like a bowl. Then the maximum point kind of looks like a dome. And the saddle point looks like that sort of like Pringle shape. And all of the flow lines tell you how to glue these spaces together to reconstruct the original space. The idea here is that if you like groups, you can think of a dynamical system as an action of the real numbers on your space. You flow through time. You might provide some initial condition x naught to your differential equation, and then you flow it through time t. And provided that you don't cross a critical value, it's a theorem that the topology of your space will not change, i.e. That x up to height b is going to be homeomorphic or really diffeomorphic to height a, provided that there's no critical points between height b and height a. Okay, that is to say, if you start here, right, this is like somewhere halfway through in our setup, this one, and you flow all the way up here, provided that you don't go through any critical points, the topology of this shape doesn't really change. It's still the same sort of shape. Okay. So let's talk about sort of a very classical application of this idea. If you think about the space of all possible loops, right, i.e. free loop space, just all the functions from the circle to your space, we can ask ourselves, well, what do the critical points look like? Well, first off, we need a function, right, if you want to look for critical points. And the most natural functions to define in this space are 1, the length of a loop. So that's just you take a loop gamma, and then you integrate over the derivative of gamma, which should give you the length of that loop. Or the energy, which kind of looks like, kinetic energy is half mv squared. This is position that should be like speed. So half mv squared, but no m. It turns out by sort of your best friend, maybe, Cauchy-Schwarz inequality, that L is less than or equal to square root E. So if you minimize energy, you will also minimize length. And in this way, the critical points of the energy function are exactly your, what you might call your geodesics, right? Those paths which are like perfectly smooth, they follow the curvature of your space. And provided that the energy is non-zero, your geodesic would be non-trivial. Because of course, if you just stay in one position and you don't move, that's also a perfectly energy minimizing state. Okay, so what does this tell us, right? It was not known for a very long time in general as to whether any arbitrary space has a non-trivial closed geodesic. Like if you start at some point on the Earth and you just sort of walk in a straight line, assuming you can, walk on top of water, or you can just walk directly through mountains, whatever, you'll eventually loop back to yourself. If you start on a sphere, pick a point here, and you just walk all the way around, you will eventually arrive back at yourself, right? Assuming the Earth is a perfect sphere. But we do know that the Earth is not actually a perfect sphere. It's kind of bumpy on the side, and you have all of these mountains and stuff like that. And of course, if you're like a cyclist and you're riding around like this, locally it looks like you're moving this way, but you might end up moving like globally, like you might end up turning around. So if you locally move in a straight line, is it guaranteed that eventually you're going to come back to yourself? So the answer is, of course, no. But in general, it wasn't sure whether there exists at least one of these paths. And it was proved in 1898 that it's true when the space is not simply connected. Don't worry about what that means. But it only took until the 1950s when Morse theory was more developed and people realized that, yes, this is genuinely true. You can find at least one. So if it took so long to find even one closed geodesic, just one loop on a space, a sort of smooth loop, it's not so surprising that it's even harder to answer the second question, whether there are infinitely many. Because of course, on a sphere, if you just move in any direction you want, you will eventually end up back at yourself. So the guess is that for any space, this should be true as well, provided it's compact, all of this. It's not known. It's still a completely open problem, surprisingly. So there are some very powerful partial results which people arrived at via things like Morse theory. Currently, it is still unknown whether even spaces as simple as the sphere have infinitely many closed geodesics. We do know that the two sphere has it, so any sphere and any deformations of the sphere, but we don't know literally any dimension above that, and we don't know all of you don't know whether the conjecture is true for all of these projective spaces. Okay. So this is sort of the actual core of this talk. Morse theory has sort of transformed a lot over the years. I think if you read some older textbooks, they still go on about handle bodies, even though this is not such a common these days. The idea here is that there's no serious difference between doing algebra and doing geometry. If you try to do one or the other, you'll hit a wall very quickly. So because of that, I'm going to have to introduce a little bit of terminology. What is Morse theory actually doing at like a categorical level? You don't have to be worried about this word. But what is Morse theory actually doing? It's trying to reconstruct the space using critical points and flows between those critical points, right? The data that you have what you might call objects, like critical points, and spaces of flow lines between critical points. If you start on this sphere at this maximum here, let's call it A, and this minimum here, let's call it C, right? We want to look at all possible paths to go from A to C, right? In this case, it kind of looks like that, right? It's just the top and then it flows all the way down to the South Pole. What it ends up looking like is like a sphere, remove the North Pole, remove the South Pole, right? And if you allow a little bit of, topology nonsense, like this is the same thing as a cylinder, right? Yep. So you just take this point and you stretch it up until it's empty, like that. Yep. So it's the same thing as a cylinder, and you are flowing down like that. And if you allow even more topology nonsense, if this is my initial condition, right? If I start at that point on the sphere, at time negative infinity, I will reach here. And at time positive infinity, I will reach here, right? So if I quotient out the real numbers, this entire thing will collapse to just a circle. Yep. So between pairs of critical points, you have a space of flow lines. And in this particular case, you get a circle, right? Between the maximum and the minimum, there's really just a circle. So the idea here is if you know this information and you know the maximum and the minimum, you can reconstruct the sphere, right? Here in this case, on the right-hand side here, you have a torus. You see, a bit hard to see here now, but maybe some of you will be familiar with constructing a torus by starting with a square sheet and then joining the two sides together and then joining the two top part and the bottom part. Maybe this is your maximum point. These are like saddle points, and this is the minimum point. I want to draw the picture. It kind of looks like this. That's a maximum. That's a minimum. And these are the two saddle points. Okay. And then you flow downwards. So forth. Because here the function is, of course, just height. Yeah, I say consider a torus. So you consider torus and you consider this height function, and you get A as a maximum point, C as a minimum point, and then you get all the saddle points.
So your V1, V2 is definitely set up.
Yeah. Okay. So the idea here is if you want to reconstruct this space, it's not enough to just take a circle and then join a point and a point. You have the white part inside here, and you have like 4 different white parts, and you have to join them all together. But the issue is you don't have the yellow parts, right? Because the path from A to C will not cross through B. Because if I start on this yellow line, I will go to B1 at time t equals infinity. I will never reach C because the derivative here is 0, right? Once I reach B1, I was stuck. I can't move anymore. So I have to modify my data a little bit. I can't just work with critical points and spaces of flow lines. I have to compactify it so that it is actually possible to start from A to C and say, yes, we also consider the ways to go from A to B and then to C. Okay, so with this data, you actually have a category if you're concerned about what that means. And so the natural question is it true? Can you really reconstruct your space using just this data?
So that called the
These are the moduli space of broken trajectories. How do you mean?
what's the long like say compactify using this program.
Yes.
How does it
What do you mean by how does it provide compactification?
okay, so this is done by program.
I think it was Chroma. I'm not sure.
So like how is it compactifying?
Okay. I mean, I'm worried that you get distracted a little bit. But I guess visually, if you want, this white thing here is going to be an open set, right? If you ignore the yellow lines and the red dots, the white thing is really generally an open set. And then after that, once you add the yellow lines, it's sort of like starting at an open interval and adding the boundaries, right? So it becomes a complex set.
When I read it, I thought it was like you got an A B line, right? So it's the I mean like so we are compactifying this moduli space, right? So this M thingy here. So this M thingy here, so you think of it like line through going from A to C, right?
Yes.
That's not line.
Are you talking about the uncompactified version or the?
Yeah, uncompactified.
Okay,
version.
sure.
So then this broken trajectory, like are you purposely drawing outside? So it looks like some boundary point to this
Yeah, exactly.
something.
Yeah. Because the paths from, for example, here, right, the paths from A to C form an open line segment here.
Yeah.
So then adding in this thing and this thing is the same thing as compactifying. Right?
So the B1 and B2 you pass through is always like say the point of index one point of
So
compactify.
of course, in this case, this is index 2, this is index 0, and in this case would be index 1. But of course, it could be index n, and any number in between. So the full picture may be if you're working in higher dimension, that you might have some critical point here of index, I don't know, 10. And by the way, when I say index, I mean that locally when you approximate it as a quadratic form, it might look something like this: x1 squared, x2 squared, all the way until x10 squared. There are 10 negative signs, right? As compared to index 0, which looks like this: x1 squared plus x10 squared. So that's kind of like the bottom part of a sphere, right? So there's 0 negative signs here, so it's index 0, and here is index 10. And in between, you could have all the possible other ways to go from the top to the bottom, right? So that can end up being quite a complicated space. So you don't get a manifold, if that's what you're worried about. You do get a manifold with corners, but that's not such an issue. Anyway, so here's the question, right? Using this critical point information, can you actually reconstruct the space? Is this actually possible? And the answer is no. So don't worry about homology. The point is, if you took a two-dimensional sphere and you joined it to a four-dimensional sphere at one single point, and you compare that to, if anyone took algebraic geometry, you're familiar with the complex projective space, so CP2. These two spaces, if you try to do Morse theory on them, are basically identical. There's no difference. It looks like there is a four-dimensional hole, a two-dimensional hole, and they're all connected. So Morse theory cannot distinguish between both of these. And that's because what's happening here is that to build this space, you start with a point. So that's what this last number is. That's a point. You attach a two-sphere to that point, right? Sorry, you attach a two-disk to that point. And then you attach a four-disk to that point. Okay? And the same thing is happening on this side. You start with a point, you add a two-disk, and you add a four-disk. But the way you attach them is different. In particular, on the left-hand side, the attachments are purely trivial. You just attach it to a point, nothing happens. But on the right-hand side, the two disks is attached trivially just to a point. But the four-disk is attached via something special. It's called the Hopf vibration. And how do we know? But Morse theory cannot detect things like the Hopf vibration by itself. So before I get carried away, and I have to do a little side plot and talk about what a homotopy is supposed to be. So actually, show of hands, does everyone know what a homotopy group is? Okay, great. So this is what it is. So how many holes does a straw have? Right. If you start with a straw, you can imagine straightening it out to look like that, and then you widen out the bottom part, right? And then you squish it down even more, and you squish it down even more until it just looks like a disc with a hole in it. So this is a straw. Really bad straw. So we can ask ourselves, what are the possible loops on this space, right? Because we now wanted to do more theory. So what are the possible loops? Well, first off, you could consider a loop that looks like that. But that loop can be contracted down to a single point, right? It's possible to retract that down to a single point. Whereas other loops, like this blue one, cannot. They go around the hole, and if you try to make them as small as possible, they'll get trapped in that hole. Yeah. Let's collect all of these possible loops. That is, if this is the set of all possible loops, i.e. functions from the circle to the space. This is the set of all possible loops. If you allow this topology thing, when you just say, I can squish it, I can stretch it, right? So this big blue loop and that small blue loop are considered to be the same. Yeah. And that's a set. It turns out it's a bit more than a set. Yeah. Consider that yellow loop over there. Isn't this yellow loop supposed to be, in a sense, this red loop plus this red loop, right? It's like you go around, so you go around once, and then you go around again. And if you take this, you add that, you get that. Isn't that a bit like taking 0 plus 0 equals 0? Because this yellow loop is also retractable to a point, right? So loops that are retractable to a point, you can call them 0. Meanwhile, this green loop here, right? You can look at this green loop, the one that goes around the whole twice. You have a loop that goes around once, you have a loop that goes around once. You can add both of these to get this. It's like saying 1 + 1 = 2. It's generally true. 1 + 1 is equal to 2. So the set of all possible loops, if you allow the squishing, is a group. You can add, you can subtract. And then, of course, correspondences are like this. This is 0, this is 1. You go clockwise instead of counterclockwise and -1, and so on. Okay, that is a group. And you can do this for any dimension. Instead of just loops, which are functions from the circle to the space, you can look at functions from any sphere in any dimension to the space. And it's surprising that this information is still sort of an open conjecture. We don't really fully understand how these groups work. There is some patterns. You'll see for S1 is Z000. That's a pattern. But everywhere else here, these are complete nonsense. Okay? All of them are finite except for the yellow ones. And then everything down here, mysteriously, if you go down the diagonal, it becomes the same. Right? Up here is complete garbage. Down here is like this beautiful magical land where everything is clean. Okay. In a sense, if you can understand how all of these groups work, you can reconstruct a space, in a sense. So let's look at some examples, right? What is I1 of the sphere? Well, any loop you draw on the sphere, imagine a rubber band on a sphere, you can always pull it back to a single point, right? Any loop. So that group is just 0. How about pi2 of S2? These are spheres on the sphere. You can imagine taking a sphere and sort of twisting it onto another sphere. That turns out to be Z. And mysteriously, pi3 of S2, this is where the Hopf vibration comes from, also turns out to be Z. Okay, diversion over. Consider, how much time do I have? Oh, I have time. Would someone like to volunteer? Ray, would you like to come? Okay. Okay. I'm going to do something, and it's don't assume the worst. Okay, I'm going to take off my belt. So anyway, hold on to this. Okay. So right now, Ray and I are a loop, right? Ray, me, and the Earth is one continuous loop. It goes through my hand, goes through him into the ground, back up through me and through him, right? So I don't want to work with just the information of a loop. I want a loop with some sort of orientation. Because look at this belt, right? It's not just a continuous cylinder. There's a flat side, there's a nice side, there's a thin side like that. What is this information? Well, the information is what you might call a framed loop. The idea is that at every point, it's not just a loop. You also have some sort of orientation. And as I go around the loop, the orientation like spins around, yeah? So there's a loop with some framing attached to it. So what is that framing? On a loop, at every point, you have an orientation, and that's 3 vectors like that, right? That's what you might call an orientation. The first vector moves in the direction of the belt, that one. The second vector is orthogonal to the flat side, right? And I can take the cross product to get a third vector, yeah? So if I twist this a lot, right? In R3, this is what's happening, yeah? There's a loop that's twisting. But in the space of these 3 vectors, what's happening is the orientation spins around, it goes through him, comes back up to me, and returns to the same position. Now, 3 orthonormal vectors, what do you call that? That is a special orthogonal matrix. Because if the 3 columns are orthonormal, then it is a special orthogonal matrix. It's determinant 1. Yeah, that's how you define an SO3. Now, here's the magic, okay? In this position, hold it straight like this. Like this. There you go. Hold it higher. So in this position, right? Let me twist it once. like that. So it's completely natural to believe that there's no way I can untwist this thing. If I try, no matter how hard I try, it will remain twisted, right? What happens is if I twist it once, that's one twist, then I twist it again, I can go through here, and then after that, the twist completely disappears. Right? And the reason that happens is because pi1, you can return my thoughts. Pi1 of SO3 is actually the cyclic group on two elements. Right? The rule is 1 plus 1 equals 0. One twist plus another twist is 0. So this thing doesn't just measure holes, it measures something else. It measures twists. It measures so much information about your space, right? And it tells you that really there are only two ways to frame a loop. One is the sort of boring one where the orientation doesn't change at all. And the other one is a sort of twisted one. And how does this relate to Morse theory? Well, it tells you how to reconstruct your space. Now, what you're doing when you're doing Morse theory is remember that you have moduli spaces of flow lines, right? Remember the sphere, you have the max, the min, and you have a circle of flow lines, right? Now, if you have more critical points, you have lots and lots of circles and lots of spheres, and you have to try to attach all of them together. And the information of how all of those things are attached is collected in what you call a cobordism. So these two circles are attached to this one circle via a higher dimensional space, right? One-dimensional. This yellow thing is two-dimensional. And the red arrows tell you that the orientation transfers onto the orientation of the one circle. Yeah? This is what you call a cobordism. And it's a group. Why is it a group? Because you can take any space, you can add itself, i.e. take a disjoint union, and then you can draw this. So it's a group where every element has order 2. You add element to any element to itself, you get 0. Yep. It's true by result of Freudian thought that if you look at the homotopy groups of in this table, you go diagonally down this table, eventually it will be the same. By some magic, it will be the same. And it was proved, I think, by Pontryagin again. So did someone ask a question? It's direct or implicit? I would say a direct limit, I think, because you have a tower. Okay. Well, anyway, by a result of Pontryagin thought, what you call the stable homotopy groups are isomorphic to the group of framed cobordism. That is to say, as long as you have a framing and orientation, and you want to connect circles together or spheres together or whatever, you have already done everything you needed to do. You have already recovered the stable homotopy group, right? And remember that the whole goal of Morse theory is to attach circles together, to attach spheres together, to reconstruct the space. Okay. So we collect everything now into something you call a framed flow category. It's even stronger than a flow category. You have the same data before, critical points, and the flow lines between those points. And you also have some notion of framing and some technical details about how to embed the space into another space. By a result of Cohen-Jones-Siegel, you can always recover the homotopy, the stable homotopy type from framed flow category data. Okay, so that's it. I just wanted to comment, my own personal research on this is about taking all of the differential stuff I described to you and throwing it away. Is to ask, to what extent can you use combinatorics to solve everything? So instead of working with smooth spaces, you imagine a computer, you might treat the space as a bunch of like polyhedra, it's like a triangulated thing. So to what extent can you do Morse theory on that kind of space? And to what extent can you do Cohen-Jones-Siegel on that kind of space? Answer is no one knows, but you know, whatever. That's the nature of open conjectures. Okay, that's it. Thank you. Okay, any questions? Oh, right. Great. You understood everything? Yes.
that they did not allow, how to say,
Yeah, sure.
draw it
Oh,
on.
you have to draw. There you go.
I saw one kind of chain I've a long time ago. The change did not allow from this to this, and then to this. It does not allow this kind of change because they say that this point, I don't know. So is this the same thing as homeopathy or is this another thing?
So from the point of view of homotopy, they don't care so much about that kind of thing. But if I'm not mistaken, I think this is genuinely only an issue up to dimension 4 or something like this. And in the higher dimensions, you have something called the weak metric. But I wouldn't know otherwise. All right, thank you. All right, other questions? Okay, fantastic. Yeah.
So that thing, like counting on the maximum minimum sample, that like always equal to the casting.
Yeah, yes, that's true. It's all the way at the start, I think. This one, yeah, it's always true. One small caveat. The only caveat is you have to choose a function very carefully because sometimes you end up with something funny. Say you had a torus that looks like this, right? Like that. And then this is my height function. Then the issue is that my critical point is not isolated anymore. This entire top part is a critical point, right? So how can I count the number of critical points now? Well, the answer is you can't. It's impossible. But you can sort of generalize the theory. Maybe the word you want to look up is Morse-Bot theory. So that instead of just critical points, every critical set can be a manifold. And it turns out the theory works just fine. So you can look at the flow that looks like that. Right? This is especially true in the free loop space case. For example, if you look at the free loop space, right? If you look at minimum points, let's say this loop is a minimal loop, right? It has the lowest energy. So it's as short as it can possibly be, and it moves at constant speed around the loop. Technically speaking, this loop and this loop are not the same loop, even though they look exactly the same, because the base point is different, right? The starting point is different. So the correct thing to say here is that there is a natural S1 action on free loop space. So every critical point occurs in a circle of critical points, right? This thing happens, but in infinite dimensions. So even in like the most basic examples, you're right that you can't really count it properly. But if you instead use information like tangent spaces, normal spaces, the count can be made to be correct. Yeah. Okay.
When usually finding these points, you look at the energy functions.
In free loop space, it's usually the energy function.
Well,
Yeah, it's easier to work with. But that's because we're interested in information about geodesics. And geodesics are critical points of the energy function. If you're interested in other spaces, of course, the function will be very different. It's true, of course, that you don't ever need to write down a function most of the time. For people who know what this means, functions on which you can do Morse theory, we call them Morse functions, are dense in the space of all possible smooth functions you can define. So it doesn't really matter whether or not you can write down a Morse function. You just know you can pick any smooth function and just perturb it slightly to get another one. Okay.
still open for S3. In the geodesic.
The question about how many closed geodesics there are? Yes, it's still open for S3. Isn't that quite strange? So does anyone take dynamical systems here? I don't know. One person. Okay. So for this one person, the reason we can even prove it for the two-dimensional sphere is because of Poincare-Bendixson. In higher dimensions, you don't have Poincare-Bendixson, and all of these results that we know using Morse theory just don't work for the sphere. Because the sphere is somehow too simple. We just can't do anything with the sphere. Okay.
People spheres that one's what windows. The only one movie.
Oh yeah, okay, great. So that's the kind of question you ask if you sort of know the answer already. So it's true that all of the garbage up here, all of this mess, is basically a complete open problem. We don't really understand it. We know how to sort of compute things, and we can use computers to compute them very high, to very high degrees. But at the end of the day, the pattern is completely mysterious. Down here, there's a very beautiful result called dot periodicity. And the idea is that if I took the SO3 from just now, right, you can imagine SO2, right, the group of 2 by 2 matrices with determinant 1. There's a natural way to embed this in SO3. And there's a natural way to embed this in SO4, and so on. Right? So in the limit, it becomes SO infinity or something like this. Yeah. They're all possible invertible matrices in any dimension with whatever. Right? And once you reach this point, it turns out that the homotopy groups of this thing satisfy a really weird. Can you still see if it's this low? Okay. Satisfies this property. If I add 8, it's the same. So it's not really clear why. I mean, depending on what kind of maths you know, maybe it's obvious, maybe it's not. But there's for some reason an 8 periodicity here at the bottom part of the diagram. I don't really get it. But it is something to do with the fact that the cobordism group, you can take any manifold, add itself, and you get 0. So why is it the diagram? This thing. This any manifold plus itself will be cobordant to the empty set. So the fact that the number 2 appears is not so surprising. The fact that it appears 3 times 2 cubed is very surprising. It's very strange. Okay. Other questions?
Since he's already mentioned about the periodicity, right? So the cobordism, do I think of it as a vector bundle it's not?
I mean, yes, so it's closely related. It's not exactly the same. So for the framing, we don't need a section, but you do need to specify sufficiently nice embedding of the space. So maybe, I guess it's the same. What I'm trying to say is you are using both normal bundle information and tangent bundle information. I'm not sure the exact relation to K-theory is I think the question you have in your mind. But
this is calculated using K-theory.
Which one? The cobordism groups?
Level.
Most of this is calculated using something called the Adams spectral sequence. So there's a way you can sort of inductively build the rest of the table using smaller, like lower dimensional parts of the table. But it's in a very unclear way. The pattern is just not obvious at all. Yeah. Okay.
So framing different, it kind of like attaching a coordinate chart at every point.
So the correct thing maybe, so every manifold has a coordinate chart already. The manifold is framed if you can attach sort of a orientation chart to it. I forget the exact way to write this, but it is perfectly possible to attach. In the case of oriented cobordism, it's SON. In the case of other types of cobordism, you can use this special unitary group. You can use any Grassmannian, and you get different flavors of cobordism, and they all work for different things. Yeah. All right. Any other questions? All right. Thank you so much.
Yeah, quite nice, right? Visual and non-rigorous. So yeah, already got something along the way. Yeah, so if you want to understand more, so you should take the algebraic topology course Nice.
Taught by who? Taught by who?
By Dr. In Kiseng. Right, yeah. Right. Anyway, yeah, basically that's that. If you got any more questions, you can hang around and chat with him and so on. Anything about life and so on. So yeah, right. Thank you all again. Yeah, right. Goodbye. Yeah.
Thank you.
Oh yeah, your bell.
Oh, my belt. Thank you.
Yes. Huh?
Should we go dinner?
What time is it now?
Yet. Have you eaten?
I also haven't eaten yet.
Yeah. Because later we got a office hour. I got an office.
I see.
So how are you going to stay until when tonight?
I can be here until 9:30 like last time.
Oh, sure. Someone pick you up?
Yeah, my mother again. She started to enjoy me coming to Shanghai now.
Because we can visit.
Yeah, long time she hasn't gossiped with her.
We'll go dinner. Okay. So, okay.
All kinds of stories, you know, she's been talking with him, say someone went to jail, this person got married.
Who went to jail? Oh,
One of my
you mean-
mother's friends.
share 那个 PPT。I mean 你在那个 group
我想上个，我想看为什么 BL 会变成第二个 seller 出来。
What is, could you repeat what this means again?
The cupboard, oh yeah, sure.
I think I rushed it.
Oh, you know, the benefit of doing things non-rigorously is that you always get through the presentation faster than you think you're supposed to. It's the exact opposite problem in White House. Anyway, concerning this set, right? Basically, that any n-dimensional space. This is all one dimension. Gamma. So just circles and like connections of circles and stuff like that. This is a group, and the group structure is given by disjoint union. So if I take a circle, I take the disjoint union with itself, I get a circle structure. Well, it turns out that of course I can do this. That. So the disjoint union of two circles is co-ordinate to the empty set, i.e. there is a two-dimensional manifold whose boundary is this. Right? This means that S1 plus S1 is 0. Yeah. So it's very strange. Yeah. In fact, I think specifically gamma omega 1 is completely uninteresting. I think it's just 0. Because of course you can just do this. What is more interesting is like for example gamma 0, right? Gamma 0 is on the 0 manifolds. So suppose you had 5 points like that, right? And this is point times 5, right? So literally point disjoint union point. And then I have 3 points here. I can do this, and then I can do this. Right? This is bad. I can even add some extra circles here, doesn't matter. But this middle thing is a one manifold, right? But locally it's a straight line, which has these as boundary. So 5 points is coordinate to 3 points, right? Which is coordinate to 1 point. Yep. So any even number of points. So any even number of points is one class, and any odd number of points is another class. So this thing is actually Z by 2. Only two. The odd and even number of points.
Just say, oh, I want 2 dots here. Must be 3.
It can be any odd number, right? Well, if it is odd, that's odd. Even this has to be even then. Yeah. Then the one that I did just now was to introduce a framing. So these circles come attached with some sort of like orientation, like that. Right? And these orientations have to join together, like all the arrows have to like match up. Yeah, yeah. Okay. So that's a group, the cobordism group. Sorry.
Yeah, I would like to ask one question. Sure. Very interesting, and I have little knowledge, but for example, in chaos theory, there is for example, like some butterflies. Look at the some, for example, some.
So do you say in graph theory?
No. In chaos theory, for example.
Okay.
It doesn't intersect itself, so there exists some, for example, there's some kind of like a butterfly. So it goes appearing loops, but doesn't intersect itself. Doesn't appear any loops, right?
Yeah.
So how to work with it? So, any, for example, any minimal energy or I don't know.
What's the question? How is this thing different from just a circle?
Yeah. Some how to find the loops because it's not more.
Is this a circle in R3? Is it,
Can't deny that.
so I think basically just a
Like a
circle in
keyboard.
R3 or how?
Yeah, in S3, for example, imagine, for example, two.
我可以打機嘛？
if you are doing
打电打要不要发脾气的？
然後之前太多人之前冰冰家人。
my how is it called this yeah.
那也是飞钱了，
读一场要读1个小时的書。
你一个这样盖嘛？
哇，这樣有排除啊，有排除啊。
And kind of killed you cannot
盖起来嘛？
find
在下面盖嘛？
some kind of like a butterfly.
Okay.
Just like itself.
What do you call this Lorentz attractor?
Yes.
Yes.
And there is not appears any loops here
这样搞啊？
because it goes infinity. So how to tackle this thing? Can we transform it? If we consider them as some kind of manifold, and by integrating there some kind.
So the issue with these kinds of dynamical systems is that they are not. Okay, so first off, this is the second order. Once you go to second order and higher, Morse theory doesn't work. It's because it's like I think
佢將 generate 那個畫面出來。
外给二面比例。
Yes.
so. If you look at that point, and you try to look locally, you cannot assign this an index because locally it looks like a point.
Yeah.
It doesn't look like a dome, a saddle, or anything.
Yeah.
So Morse theory fails for higher than first order.
Oh.
Yeah.
Okay, thank you.
Yeah. So you have a.
No,
Oh, yes.
no, go back to
That's fine. It has some.
一样啊。
I'm not very familiar with the applied side, but it has some applied applications because, of course, critical points are of like dynamical systems are very important. The one I know is that have you heard of like topological data analysis or something like this?
I didn't take the topology.
Oh, okay.
Not even.
这样搞。
Well, in that area, there's this tool called combinatorial Morse theory, and the idea there is that you can reduce a lot of information to very little information using critical points. Like for the sphere. Oh, it's gone. Well, for the sphere, you have a maximum point and a minimum point, right? And since you can reconstruct the sphere from two pieces of information, who needs the entire sphere?
Right. Study the critical point.
Yeah. So it's a sort of like data compression technique. No, the correct word is it's it's a dimension reduction method. Yes. So I think it's not a very popular one. These days, if you do like high dimensional statistics, I think the correct the most popular one now is something called UMAP or something. Is it UMAP? I want to look up this word. Yes.
Oh, this is really.
So good question. This is the thing, uniform manifold approximation projection. So this is a very common. This is a very common applied maths thing. Like it's used basically everywhere in like high dimensional statistics. Like everywhere. Like genuinely, like a lot of AI stuff. Instead of trying to deal with like all these gigantic high dimensional spaces, they use UMAP to reduce it to just like 3 dimensions. It's a bit like using what's the word for it? What's the word when you reduce to only 2 axes or something? Principal something. Principal component analysis. Yeah. So it's like a more sophisticated principal component analysis. Does that answer your question? I kind of rambled because I know it's the task part. So anyway, what was the question?
I think so.
In a lot of ways. Oh, sorry. I wasn't supposed to erase that. Sorry, I erased that by accident. The combinatoric side of things is that if you're working with a computer, supplying a sphere to it is like infinite dimensional, right? It's not working. Yes. Huh?
Yeah.
Oh, I'm pretty sure the diagram on the left is like technically wrong.
That one, huh?
Yeah.
Wrong.
I think it's not actually meant to be. So that's just illustrative.
Okay. This would be this.
Huh?
This is the correct one.
No. This diagram is wrong. This is not even a morph function.
This is not a morph function.
Yeah, because look, you have a gradient flow line from a degree 1 to degree index 1 to illustration. You're not supposed to have that.
Okay.
So this is a degenerate thing.
Okay.
So the correct thing to do is to just like tilt it slightly, and then if it becomes one there and another there.
Like a space.
It goes here.
It's very
Yeah.
The point why like now when we try and flip it, it's like when you glue your circle together, why seems like this two
The diagram, the sheet that you
so like here you are
What do you mean by if you
glue top and bottom.
your V2 will be a bit.
Then you yeah.
correct? So you
Yeah.
is it that
因为我那个不是看
the torus is that you might know like the what happens?
But it should like something like
this point
要换两个椭圆形的方式，那就是椭圆形的本来是椭圆形的嘛，好像你的 base
So I think it was the geometry. So like we really is different from this.
Yeah，我记得那个时候 get
You can glue this into this in many different ways.
只有你的 base
We only say that
这个 surface，
so the actual height is actual embedding into R3 is different.
好像 pendulum sin theta，因为它同
So
时
this is the torus is 2. But if you
you just say that they are about 他在想
yeah.
在来so it's not about
Okay, so any more function wise, in order to get height, what you do is you
因为这是一个 limit cycle，
and the point is you can perturb the space until the height is so the diagram is actually wrong. So this is not actually a
not match up with most functions.
yeah, but
我现在可以在这里讲清楚
yeah.
Your most function.
Okay, wait, sorry, I have a question on this one. Wait, sorry, someone was answering someone's question. Sorry, my bad.
It's okay, I get carried away.
So,
If you stop recording,
oh, yes. I'm going on.
PCA
How do I open this? What's happening?
PCA
这个东西的什么啊？那个什么
How do
apply 的
现在 laptop
I just stop sharing and then
bro
stop recording again?
啊
这个 bro
PCA
Okay.
有趣的。
So